excited to be here. So I did my PhD here, actually, and I've been gone for a year or so. And I've been always looking for an excuse to come back and have the great food in Berkeley. So thank you for organizing this symposium. And also, it'll be great to learn about what's going on in remote sensing and how it relates to development. So before jumping in, I want to acknowledge my co-authors, so Nicolas Vis and Amaury Tillemont from Laval, Jim Yoon and Steve Gorelick from Stanford, and Hua Zhang from A&M. So I'm a hydrologist, so my bread and butter is to predict water resources, and I'm particularly interested in how water may or may not interact with violent conflicts. And so when you're doing this kind of work, you may not want to go in the field too much, in places where there may be a conflict pretty soon, or there is already one. And so in that sense, since there's no in-situ data available, remote sensing becomes a really valuable data source. And so what Joe was telling this morning really resonates with me, because in that case, you really have to only use the data that's taken remotely, right? There's no real ground truth you could base your analysis on. So the case we're going to talk about today is in Syria. So Syria shares a very strategic watershed with Jordan and Israel downstream. It's the Yarmouk Basin. It's a tiny rivulet, actually, that big. But there's about 33 known dams in Syria who's upstream. And so everybody's a bit nervous around this tiny river. And the Jordanians that are downstream have been seeing the flow that's available to them decrease steadily over the last few decades. But very recently during the Syrian conflict, actually, the trend reversed, and the water available from Syria actually increased a bit, quite a bit, actually. So of course, like the immediate link you could draw is because people moved away from Syria because they're refugees, right? They didn't use the water anymore, and so water increased. But at the same time, there was a huge drought that hit the Middle East in the early 2000s that many people say actually kind of spurred the whole Arab Spring thing, including the Syrian conflict. And so this drought receded almost at the same time. And so there's a big question of whether these changes in the stream flow that are of strategic importance regionally are human-caused or ends or climate caused. And so that's what this study was about. And so since it's a seasonal climate, so it rains in the winter and it doesn't rain in the summer, the way people do agriculture there is by storing as much water as they can in irrigation dams. That's why there's 33 dams over there, and use them in the summer to irrigate crops. And so being able to detect and monitor how much water is stored in the reservoir was a key part of the study. So how would you do that? Well, you could see the water from imagery, right? So that's easy. You could detect the water extent and monitor it day after day, or depending on the frequency of the data. And of course, there's a trade-off between temporal and spatial resolution that's going on. But what's difficult, though, is that we're not interested in how much surface area of water there is, but how much volume is stored. And so you have to take into account the topography, which is not, reservoirs are not like water buckets. It gets pretty complicated. And so there's a non-trivial area-volume relation. So people have attempted to account for that using specialized radar altimetry that are mounted on some of the satellites. It kind of works, but due to technical limitation, you could only do that for very, very large reservoirs, like big lakes. And so these reservoirs in Syria are tiny, like a few hectares, and so you cannot really use these techniques directly. So what we did, we developed a new approach to kind of combine satellite imagery with digital elevation model, and those two sources can be used to correct each other to get at the volume without actually having to go there to do a bathymetric survey. So first we classified pixels as water or not water. Then we combined those results with a digital elevation model to correct the digital elevation model. And then we reconstructed areas that are hidden by clouds or technical issues. So the first one is pretty straightforward. There are all these indices you could use to detect water. We use several of these indices to kind of correct and amplify each other to detect water. So we're pretty confident we're able to detect water surfaces on a monthly basis here. And then we needed topography to construct the area volume curve. So that was the main challenge, right? So you could use those DEM that are available out there, you know, the global 30-meter resolution aster, for instance. But the issue with that is that the precision, the vertical accuracy is on the order of 10 meters. So if you're in the middle of the Himalayas, it might not matter that much. But if you're in a flat place, like the Syrian plateau there, well, it matters a lot. And so what we did, we basically used Landsat to correct the digital elevation model under a simple principle that if a pixel is often emerged, it's probably going to be lower. And so you could detect and kind of have an idea of the relative height of each pixel by looking at how often they are in the water, basically. What was important here is that since they're irrigation reservoirs, they were empty at least once during the whole period. And so we're able to actually get the full area volume curve, which allows you to get at the storage as opposed to the storage difference between the year. And then there were some stuff that we had to correct for. So for instance, cloud, it's rather difficult to distinguish between cloud and surface area on satellite imagery. And Landsat 7, which we use, has this annoying feature there. So one of the sensors got broken, basically. And so most of these images have stripes with no data, so we had to correct them, because if you're looking at the big reservoir, it doesn't really matter that much. It's like a tiny little stripe, but these reservoirs are small, so it really mattered. So what we did, basically, is we took all these pixels where we didn't really know what was happening, and we looked at their elevation as given by the digital elevation model that was corrected. And so it's important to mention here that the SLC failure here moves from image to image. So the pixel that you don't see change from time to time, so you could actually do this correction. Okay, so that's the end result. And we had data given by the Jordanian Ministry of Water and Irrigation on Reservoir in Jordan. And so we were able to use the storage data to see if we're off or how bad we did, basically. And it turns out we didn't do too bad on average. So that was pretty encouraging. And so the next step was to apply that into Syria to have a look at what was going on. So to give a bit of background, there was everybody has heard of the Syrian conflict, I imagine. There was a big immigration refugee crisis that was going on with millions of people moving out of Syria, and many of them actually moving from Syria to Jordan. And so the Yarmouk Basin is right here. In the middle of it is the city of Daraa, where many people think that the Syrian conflict actually started. So there were demonstrations and public unrest there, and that's what spread to the rest of the country. And it's a highly strategic region for Syria and for the Middle East, because it's one of the headwaters of the Jordan River. And if we look at satellite nightlight, it's pretty obvious that people moved out, right? So we have Jordan, the Jordanian part of the basin down south here, and the Syrian part. And if we look at year after year, the average nightlight imagery, we could really see that it decreases in Syria and not in Jordan. So this is it's a pretty good qualitative display of people moving. But we wanted to get more quantitative. And if we looked at the flow, we could really see that in 2013, where most of the refugees actually moved out, the flow basically increased by threefold. So there was a dramatic increase all of a sudden of the flow into Jordan. So we did this analysis on the reservoirs, and in order to have a counterfactual, we used the Golan Heights. So it's technically in Syria, but it's occupied by Israel. And so the reservoirs that are there, they are presumably managed by Israel and therefore less impacted by conflict. So we did the analysis. In red, you have reservoirs in Syria, and in blue, you have the total storage in the Golan Heights. Little dots are monthly values, and we did that for every year. And we could really see that the droughts that happened actually impacted storage, and then they recovered, and then they decreased. But you could see that it decreased much faster in the Syrian part of the basin. And actually, if you do a difference in difference analysis, which this data allows you to do, you could see that there was a significant 50% decrease in reservoir storage in the Syrian Yarmouk after the refugee crisis happened. That did not happen in the Golan Heights. We did the same thing with irrigated land use. So it's a Mediterranean climate. So in order to detect irrigation, you just look in the summer. Whatever is green is probably irrigated, so it's very, very easy. We did that again for Syria and Jordan, using Jordan as a counterfactual. And here the trends are even more dramatic. So you could see agricultural development until 2006 or so. Then the drought decreased the amount of water available, so decreased irrigation agriculture. Then it recovered a bit. And then irrigated agriculture decreased dramatically in Syria, but not in Jordan. And again, with the difference in difference analysis, you could see that the relative decrease is 50% due to the conflict in Syria. Now, putting that together into some sort of large-scale water balance model, we're able to say that about 50% of the 350% increase of the flow is due to people moving out, and about half of it is either due to something we don't know of or to rainfall that have increased. So we published that, and people got interested, and there was quite a bit of press on it. And many of these journalists, they said, you know, one of the titles was like, "Rivers overflowing in Jordan because of the Syrian conflict." And so like, whoa, this is kind of, I mean, it gets political. So it's important to actually put that into context, into the wider regional context. So first of all, even though the water available to Jordan has increased by a little bit compared to historical levels, it's actually very tiny. So here you could see historical inflow into Jordan, into the Al-Weda Dam, so the dam that's at the border, in black here, so it decreased quite dramatically. Then there's a little bump, so that's what we analyzed. And then our co-authors at Stanford actually plugged a climate model in order to kind of predict in this different scenario how the Yarmouk River will evolve. And we could see that under all the scenarios that under the most extreme scenarios they analyzed, it never actually recovers historical levels. And Jordan and Syria have entered into a series of agreements that guaranteed a certain level of water for Jordan that was not upheld and that will never be, it seems. Secondly, and importantly, of course, many people moved into Jordan, and so Jordan has a much higher water demand that has to be accounted for. So even if the water would have been able to be used by Jordan, they would have to use it to feed the refugees. So you know, it's not really a win situation. And importantly, the water actually arrived in the Al-Weda Dam there, but most of the people in Jordan live on the highlands. So Jordan does not have the actual infrastructure to pump the water up there. So even if there was more water, even if the increased water would be sustained in time, it would just, you know, they could use a little bit for agriculture in the Jordan Valley, but it's mostly water that would be just flushed down to Israel. They wouldn't be able to use it to actually feed the people. All right, so to conclude, I thought it was really cool that we could use satellite data to actually do science in truly inaccessible regions, where there's war or where there's natural catastrophes and stuff like that. I think there's a big scope to be able to use them to actually do some predictive and causal science in those regions. And for Syria, it was interesting that the effect of war-related migration and regional water resources was really there, and satellite data allowed us to actually distinguish it from natural effects, and so that was an interesting outcome of the story. So the methods are published in a paper that's currently in peer-reviewed in hydrology and earth system science, and the specific story on Syria was published last year in PNAS. Thanks a lot for your attention.